Hello, everyone. My name is Molly Halsey, and I'm the event specialist here at Enterprise DB. I will be your host today for our webinar, Programming the SQL Way with Common Table Expression. I'm joined by Bruce Momjian, co-founder of the Postgres SQL Global Development Group and Database Architect at Enterprise DB. Before we get started, I just want to go through a few housekeeping items. This presentation is being recorded. We will be sharing the recording along with the slides after the broadcast. The lines are currently muted. If you have a question, please feel free to submit it in the question panel. Today's session is scheduled for 1 hour. We expect the presentation to take most of our time today, and we will allot extra time for Q&A. If we do not have time to address all questions, we will follow up afterwards with an attendee whose question was not answered. Today, we are doing a giveaway of socks. So if you would like a pair of Enterprise DB socks, ask us a question in the questions box and send us your address, and we will try to get socks to you as fast as possible. Along with that, we are sending it out to anyone in the U.S. So if you are located in North America, in Canada, U.S., let us know. We will get you a pair of socks. And now, without further ado, here is Bruce.
Great. Well, hello, everybody. Good to talk with everybody today. My name is Bruce Momjian, one of the Postgres core team members, and I've been with Enterprise DB for 13 years. It's my pleasure to talk to you today about common table expressions. But just to get started, we want to tell you a little bit about Enterprise DB. I guess that's the commercial part, Molly, huh? So we have had some interesting seminars up to this point. Some of them recently related to installation. I was in the JSON one last month, and that one was really good. We do have one coming up on the 20th related to Kubernetes. I think we're looking at one for December, Molly, although we're not positive yet, but that one sounds kind of interesting, maybe related to monitoring. So we shall see. But today is common table expressions, and this is a pretty big topic. A lot of slides, but I think you'll be able to handle it, and hopefully you'll learn something. Enterprise DB, again, I've been around since 2006. Company started 2004. Basically, we are sort of the enterprise Postgres company, as we call it. The big focus of the company is to provide enterprise solutions, tooling, migration assistance, migration tools to help enterprises use Postgres efficiently within their enterprises. So it's kind of fun to be here. My major job is a community person, so I'm not as involved. Actually, I spend a lot of time in the community, going to conferences, reading email, writing presentations. Obviously, it's a lot of fun. Enterprise DB has been again well recognized as a community member. It's in the Gartner Magic Quadrant, which I believe is the next slide there. And we do have some pretty interesting Postgres people who work for us. I think that's the next slide. Yeah. Oh, no, I'm sorry. This slide's kind of interesting. Back up, Molly. This is interesting because, you know, I've been with this company for a while, and obviously, 13 years, we're still growing, right? We have roughly 20% of the Fortune 500 and 15% of the Fortune 2000, which is good, but it means we still have a long way to go. Oracle's helping us a lot by sort of doing what they do sort of clumsily, and obviously Postgres is becoming tremendously popular. And our Postgres people, which we have on the next slide, kind of gives you an idea of what we do. We have a lot of people who Enterprise DB, our company, invests in them working in the community, and obviously keeping the community healthy, growing. We just had a major release, Postgres 12, last month. I did give a webinar about that, I think in September, so you might have seen that. But that release is out. I think we're putting out 12.1 this week. The dates are on the website. It might be this Thursday. I think it's this Thursday. So Again, we're kind of chugging along. We're working on Postgres 13 already. I'm processing tons of email every day, trying to get ready for that and make sure that we have another exciting set of features for Postgres 13, which again is due out in September, October of 2020. So what I'd like to do is to launch into the presentation and the material. I'm just going to hit that, let's see here, button there. And there we go. Basically, this is a presentation about common table expressions. It's kind of interesting. I wrote this talk, I want to say a couple of years ago, but I think it's incredibly useful. If you want the slides to this presentation, Molly, I think we're going to be sending everyone the slides. But if you want to follow along, good. Or you want to look at some other presentations, the URL at the bottom is my website, and there's probably 20 or 30 presentations there, along with a lot of video of like giving the presentation. So that might be something to do after the talk if you really like what you heard and you want to hear more. That's kind of how you would do it. So what are we going to talk about today? We have 96 slides, so I know it's a little daunting, but we'll chug through those pretty quickly, and I want to give time for questions. What we're going to talk about first is the concept that's more of a computer science concept of imperative versus declarative languages. And you might think that's kind of an odd thing to start with in a database talk, but in fact, it is pretty relevant to how you look at common table expressions and what they mean to programming capabilities within SQL, which again might sound kind of cryptic, but once I kind of get going, it should be pretty clear what I'm talking about. Okay. Then we're going to look at the syntax of common table expressions. What does it actually look like? Then we're going to talk about recursive common table expressions, which is probably the most interesting type of common table expressions. And then we're going to launch into a whole bunch of examples. It's going to start really easy. That's why I have 96 slides. It starts really slow. But by the time we get to the end, your head will be spinning because there'll be a lot of really interesting ones. We're also going to talk about writable common table expressions, which is a Postgres extension. And finally, we're going to close out just with a summary of why to use common table expressions. Okay, so let's get started there. Okay, imperative versus declarative languages. So again, I promised a little computer science lesson. Imperative languages, there's basically two types of programming languages. Imperative languages are languages where you describe the computation that you want to have performed. Most languages that programmers work in are imperative languages. So C, Perl, Python, Java, JavaScript are all imperative languages because you're instructing the computer what to do. And a lot of people are obviously very comfortable with this. This is kind of like that's the way we think of programming, right? As programmers, this is the way we think. But SQL is not an imperative language, which is why we're actually talking about this. So in declarative languages are different. There's only a couple. Frankly, SQL is probably the most popular declarative language I can think of anyway. A declarative language, you express what you want from the computer, and the computer figures out how to give it to you. There's a bunch of reasons why SQL is popular as a declarative language. It has to do with the heavy reliance on data and the speed at which data can be accessed. The idea that the optimizer is a huge part of why SQL is popular, because you can declare, I want to see some data, and the optimizer will figure out, based on the constants that you provide and the data layout as it currently exists, it will automatically tailor how it gives you the data in the most efficient manner. And that's really why SQL is one of those outliers as a declarative language. And I have an optimizer talk that explains a lot of the details about how Postgres and other databases do that. But the concept is that imperative languages are what you normally think of as a language, and declarative languages are kind of these outliers, and SQL is one of them, where you declare what you want, but you can't actually tell it what to do. Okay. So these are examples of imperative languages. I gotta have the basic example right at the top there, but basic C and Perl. Basically, this is just printing the word hello over and over again. And as you can imagine, you're imperative. You're telling the system what to do. In declarative language, a little different, right? In fact, I'm trying to reproduce what I did in the previous slide here in SQL, and I can't do it. What I'm trying to do is print hello and hello over and over again. The best I can do is to print 4 of them or 5 of them or however many I can type. Because it's difficult to implement something that is imperative, like an infinite loop, in a declarative language. Just kind of makes sense, right? Because you don't have the control in a declarative language that you have in an imperative language. Now, you can issue, well, why would you want to do an infinite loop? I understand that. But there are a bunch of cases where you want to loop a certain number of times, or you want some type of control, very fine-grained control over how the data is being processed. And typically, in an declarative language, you don't have the ability to do that. Okay. So again, imperative languages, when you're writing with libpq in C or Java, JDBC, or you're using PL server-side languages like PL Perl, PL Python, those are imperative languages. When you're using common table expressions, though, and that's the highlight at the bottom, that's what the topic of this is about. And what's really unique about what's happening here is that a common table expression is one of the few areas of SQL, which is a declarative language, where you actually have imperative capabilities. I'll say it again. Common table expressions, although it's part of the SQL language, which is primarily imperative, is one of the few cases where you can actually, which is declarative. Common table expression is one of the few cases where you can actually have imperative control over your data. And that's really what this talk is about. So let's take a look at exactly what the syntax of common table expressions are without getting fancy, just the basic ones. And then we're going to launch into the sort of imperative capability that common table expressions bring into the SQL language toward the later slides. So this is what the syntax looks like pretty much out of the SQL Postgres manuals. It always starts with the word with. So the word with here, obviously indicating that that this is sometimes common table expressions are referred to as with queries because they always start with the word with. Then there's the optional word recursive here. And then we have a common table expression name. And in this case, it's labeled with query name, but you get the idea. Every time you use a common table expression, you're going to want to name it. Then you have an optional column list in parentheses, and then a select clause inside of parentheses. That's what we're doing right here. Okay. And then an outer select clause. So again, the word with starts it. Optional word recursive, then you name it, optional column list. Then you have a select or other query inside of parentheses, and then a select outside. There's going to be a lot of slides here. So one of the things that you need to remember is to look for the red on the text. Okay, so when you look here, what do you see? You should be seeing the red, because this is a simple one, but once we get to slide like 30, you're going to be looking at this query like, what am I supposed to look at? You should be looking at the red parts of the query, okay? So here is the simplest with query or simplest common table expression I can give you. Starts with the word with. The name of the common table expression is called source. And then inside the common table expression, inside of parentheses, we have the query select one. Okay, that's all in red. So the common table expression part of this query is that red part, which starts a word with, it's called source, and the query is select one. It begins with parentheses, ends with parentheses. Now, every common table expression has one or more of these with clauses, and then has a final clause, which does not start with the word with, which is a normal query, which typically references some or all of the common table expressions above. So, as you can see, I called the common table expression source, and you can see in the black query at the bottom, I say select star from source. So the source in the source, it's part of the black query, and the source that's in the red query, that's the same name. So I'm referencing source. I'm naming source on the first line, and on the fourth line, I'm actually referencing the common table expression that was above. Okay. If you're curious about this presentation, you want to kind of run it yourself, at the bottom there in pink, I have a URL. You can actually download the SQL that you're seeing in this presentation and run it by just piping it into PSQL or running it in the query tool. So again, if you're curious about this, you don't have to cut and paste it. You can just download the SQL and just run it. Okay. Here's the first feature I have that I wanted to show you, and that is that I can name the columns inside the common table expression. Because if I go backward, notice that this query result here, which is 1, because the 1 here goes to here and to here and to here. This 1 becomes source, and this source is 1 and it comes. But notice the label is column with a question mark, so it doesn't know what the column name is. But I can name that column. I can name that column inside the query that's in the common table expression. I'm calling it col1. As you can see, it's returning a label called col1. I can name the column inside the with clause. So after the word source, I can put a column name up top, okay? And then, as you can see, I get column 1 at the bottom, okay? I can even do it this way, and this is a little crazy, but hey, I'm crazy, right? What I did was I named it col1 inside the query in the common table expression. I named it col2 in the with part of the common table expression, and I labeled it col3 in the final part of the query, and you see col3 is the one that wins. But again, this is just to illustrate the naming of how it works. It's always the last one that wins, the outer one, okay? I can return multiple columns, so here I'm returning 1, 2, no big deal. I can, let me just remind you, as we're going to get a little more advanced, I want to remind you of a behavior of the union clause. Okay, so the union clause at the top, the union clause by itself will always remove duplicates. That is a function of union. It's a function of the abstract, the relational calculus that is part of database theory, so that when you do select like this, select 1, union select 1, you get only a single one out. If you add the word all, then it does not do the removal, and effectively you get it does not remove the duplicates. And once I get to the next slide, as I get to future slides, you're going to see why that's important. So I'm just reminding you of this difference between union, union, all. Okay. So let's actually use union all here in one of our queries. Now, this is the first case where I am actually using 2 common table expressions, source and source 2. Source returns 1, 2. Source 2 returns 3, 4. So in the bottom, I say select star from source, union all, select star from source 2, and you can see that it's kind of combined them together, right? I used union all. I didn't have to, but I didn't want the duplicate removal to be happening, so I just used union all here, okay? Here's a bigger example. This is a lot more, I think, realistic. So now, instead of returning constants, we're actually doing a query inside of the common table expression. So we're doing a select from PG language with a join clause on PG roles, and we're returning language name and the role name inside the common table expression. That is called source, and at the bottom, I'm returning source. Now, this is kind of a silly example. Like, why wouldn't you just run the query in red? Why would you do all this other stuff? It seems kind of useless, right? But what about this? And here's we're starting to kind of walk into a case where we're actually using common table expressions for some value, okay? So I have the same query at the top, select source as whatever. And I've added an order by in the query at the top. Okay. Then what I'm doing at the bottom is I'm saying select star from source, which is what we had before. But then I'm saying, and this is why the union all is important, I'm saying union all, select the minimum language name and give that to me as the last line of my query. So the unique thing about what we're doing here is we're actually referencing source 2 times. And this is where the word common table expression, the concept of common table expression is that you effectively can reference it in common several places. And this is kind of the first example of that. There's a lot of examples coming, but this is like the trivial example. Here's a bigger example. I have created a class common table expression, and now I am joining the class common table expression to the attribute table. And effectively just kind of taking a query that normally would be part of the bottom query and basically kind of merging it in with another query. So I've kind of taken the PG class query and I've broken it out into a separate query, and now I can reference it kind of on its own. So not a super exciting, but you kind of get the idea. Okay. All right, so let's go back to imperative versus declarative. Now there is this imperative control in SQL, which we're going to kind of combine with common table expressions in a couple slides, and we're actually going to be doing some really interesting things. But I want to just review for people the case statement. Remember, I already reviewed union all. Let me review the case statement. The case statement is sort of like an if statement in SQL. It is imperative because you're controlling kind of what it does. So, for example, at the bottom here, if I want to print the word positive 0 or negative, I can effectively use a case statement here to do that. And it gives me sort of an if control. It's not a loop, it's just an if statement. Not super exciting, but you kind of get the idea. Okay. So, let's talk about the sort of really interesting part of CTEs, and where CTEs start to become imperative is with recursion. You've probably heard this term before, recursive CTEs. Maybe you weren't sure what it was. Some of the relational database, most of the relational databases support recursive CTEs. There was some syntax prior to the standard, which also were kind of recursive, although it had different names. But this is kind of the standard everyone's using now. Okay. So as I said before in the early slides, the word recursive is effectively the special word that we add after the with clause. You remember seeing that as syntax, where we're now saying that we want this query to run recursively. So what we're going to try and do is, as you can imagine, with recursion, we're going to create some kind of looping here. But this example doesn't work. Okay. This example doesn't work because effectively, to have recursion, you have to mention the function name inside of the function itself, right? That's the way recursion works. Like doing a factorial, the function's called factorial, and inside the factorial function, you call factorial again, right? That's what recursion is. And you look at this example, it doesn't have it, right? The recursion, the function call or the function name part, it's called source, but effectively, what are we doing inside of source? We're doing select 1. And what does it do? It just returns 1, doesn't do any recursion. Okay, that's not what we want. This is what we want. Okay, and I've used statement timeout so it doesn't run forever because it would. So don't test this on a production machine, at least without the statement timeout. So effectively, what I'm doing here is I'm saying with recursive, and I'm calling source. Okay. And then inside the parentheses, here's that union all thing we looked at before. I'm doing select 1, and then I'm saying union all, select 1 again from source. So as you can see in red, I've got source as my function name, my recursion common table expression name, and then I'm selecting from myself. This is exactly the way recursion works. Okay. Now, this is a completely trivial example. It never finishes. It doesn't even print anything because it never finishes. Okay? So this is not, this is not a great paradigm of exactly how you want to do common table expressions. But my point is that when you create a query with this structure, it allows you to have imperative control of SQL. And for the rest of the slides, I'm going to show you actual useful reasons why recursion is useful, how it works, how to use it in a whole bunch of different cases. Okay, so I promise this may be the last useless slide. So exactly how does this work? So I've kind of labeled it. Effectively, the way the query is run is it's almost always in this format where you've got some constant or some initialization value, in this case 1, and then you've got a union all, and then you've got a second query which references the output of the common table expression. So the select 1 goes here. It comes down to source, so the 1 effectively comes as this part of this select. We select another one, it goes up, and in this case, because of the way we've written it, it just continues repeating. But the point is that the primer value, the initialization value, is what kind of starts off the second query. So think of that as sort of your sort of bootstrap number, and that actually gets fed into the second query, and then the second query does some stuff, and it continues doing stuff until it stops getting data. And actually having it stop getting data is something we're going to show you very soon. So this is another example of the infinite loop, which doesn't finish. Instead of selecting 1, I'm selecting the word hello, which again doesn't help me at all. It's just the word hello. Okay. If I used union, notice I use union all. Now, if I use union here, it finishes right away. Why does it finish right away? Well, because the hello goes in, it gets another hello, and it's like, oh, I already have a hello, so I'm not going to generate a new line, so I'm done. So there's no recursion here. The recursion stopped because a duplicate has appeared. And because I've used union instead of union all, it kind of stops the recursion. Now, there are some cases where you may want to use union to prevent recursion, particularly if you've got a data structure that has duplicates in it, or you're walking a tree, which could have a loop in it. This union capability, which I'm not going to talk about a whole lot, but sometimes you may want to use union. Most cases, you're going to want to use union all because you want control of what's going on. But there are cases where, to prevent infinite loops, union actually in a common table expression is a useful capability. Here's, I think, the first programmatic imperative presentation of common table expressions. Effectively, what we're doing is we've created a recursive query with the name source, and what we've done is we have a seed value of 1. So the 1 goes up into source. Source is referenced down here. So the 1 goes up here. It actually goes into here, comes out as 1. 1 plus 1 is 2. Is 2 less than 10? Yes. So it goes back up, comes back, 2 comes down. 2 plus 1 is 3. Is 3 less than 10? Yes. Goes back up 4, all the way around until it hits 10, and that is the output. Okay. First example of actually using imperative capabilities SQL to generate the numbers 1 to 10. Do you really need to do that? No. Postgres has a function called generate series, much more efficient, much easier to use. But you kind of get the idea. We've got all of the elements here that we need to create a common table expression. First, the initialization value, which is 1. Second, we've got the recursion going on because we reference source in the query after the union all. And third, we have some kind of termination value. So the termination criteria is counter less than 10. As long as it's less than 10, it keeps going. When it isn't less than 10, it finishes, and that's exactly what we get here. I'm going to be showing you some of examples in Perl. I'm not sure how many of you do Perl, but some of the examples later on are going to be kind of complicated. So what I've done is I've taken this common table expression, I've re-shown it as what it would look like in Perl. Okay, so again, a very simple example, printing 1 to 10. Okay, but in fact, it doesn't look like that in Perl. Really, this is a This is a non-recursive example. This is really what it looks like in Perl. You create a function f, you prime it with 1, because we primed it with 1 down here. Okay, the 1 goes up, it gets pulled into arg. As long as arg is less than 10, it returns, it calls it again with 2, again, all the way out to 10. So again, this is a Perl example of exactly what this, so that's an imperative example. That's an imperative example of recursion doing a counter, okay? This is even a more accurate example if you're really a Perl person. The reason this is a more accurate example is because it accumulates the numbers in an array called table, and it appends or pushes the values onto the array. And that effectively is the way that it's working internally. It really doesn't output them as this print command does. It actually pushes them onto a stack and then prints them after the result has returned, after the function is returned. So again, kind of interesting if you're really into that kind of stuff. So those are all of the kind of underpinnings of what I want to talk about for common table expression in terms of syntax, behavior, things to look for, terminal conditions, recursive capabilities, initialization values, and so forth. What we're going to do from now on is I'm going to show you actual examples. And we're going to start out really simple. So here is an example of a factorial. Everyone remembers maybe factorial from mathematics. Factorial of 10 is the numbers from 1 to 10 multiplied by each other. So our initialization is 1, 1. We have 2 return values, a counter, which you saw before, and a product. The product is effectively the counter plus 1 times the product. It's accumulating. And then at the bottom, we return the counter and the product. So if I say counter, if I supply 10 here, 10 is our terminal condition, this is generating all of the factorials from 1 to 10. Now, you may only want the last row, the final row, and what we did is we added in red here some restriction in the outer query to say, you know, I realize you're generating 10 rows, but I only want one of them, so I'm only going to return the 10, the last number. Okay. Here is an example in Perl of doing exactly that. Same structure, initialization values in red, the second recursion also in red, and we're pushing it onto an array, and then at the end we print it. You can do string manipulation, so we can do more than numbers here. What I'm doing is the letter A, and I'm appending the letter A repeatedly 10 times, and I get NAs, like 1, 2, 3, all the way down. Okay. I can actually compute my characters, so instead of doing A all the time, I can do A, B, C, D by using char and substring and ASCII and so forth. So what I'm getting here is I'm getting A, B, C, and so forth all the way out to J, A to J. Okay. I can do ASCII art. So in this case, I'm going from minus 10, which is my initialization value, to plus 10. Can you see that? The first red, minus 10, the last terminal value, less than 10. So I'm basically going from minus 10 to 10, and I'm going to print a specific number of spaces with repeat, then an X, then concatenate number of spaces and an X. And I get this. Kind of cool. Now maybe you let's break this out. So what I've done is I've kind of separated it out, and you can actually now see the numbers from minus 10 to 10 on the right and left-hand column, and again the different number of spaces and the number of X layouts on the right-hand side. Maybe you don't like that. Maybe you want a diamond instead of an X. If I change the way that I do my spacing, I get a diamond. Maybe you want a more rounded output, so I'm going to put an exponentiation in here based on the number of spaces, and I get what looks like a football to me, or maybe a rugby ball, or hachapuri if you're familiar with Georgian breads, cheese bread. That's kind of what it looks like to me. But again, it's sort of a different kind of, so you can do all sorts of cool stuff here. I can do a circle by doing a little different exponentiation. It's not a perfect circle, but you kind of get the idea. You can sort of see we now are in the imperative. If I can actually draw images in SQL, we're absolutely in the imperative behavior case here. Prime factors, again, another very classic computer science exercise. We want to take a number, we want to print its prime factors. I'm not going to go into a huge amount of detail here, but effectively what I do is I supply a number, in this case 56, and I run it through looking at whether there is a remainder in the division. And if there's a remainder in the division, then it's a factor, and I divide it out. And I keep going until the factor is 1. So effectively, I take 56 and I run through a bunch of numbers. You can see the numbers on the left, 2, 2, 2, 2. As long as the number divides, I keep using it. And then 3, 4, 5, 6, 7. Once I get to 7, you can see I run out of remainders and I can stop. And on the right-hand side, I determine whether it's a factor or not. So I can now run the same query, but only output the case where the factor is true, and now I get the prime factors of 56, which is 2, 2, 2, and 7. I can do a factor of just a random number. I pick 3, 2, 2, 4, 3, 4, and I get, surprisingly, a similar output. Pretty clear. I didn't know, when I guessed the number, I didn't realize 853 was going to be a prime, but it obviously is. Factors of 66, going back to that example, you can see there's a whole bunch of duplicates here where we're kind of running through a whole bunch of falses that we could not really create. So we can kind of optimize this by exiting, by only doing evens after 2. So we can do 2 odds after 2. So we can do 2 as many times as we want. Then from after 2, we would just do 3, 5, 7, 9, and so forth. And you can see now this is a much cleaner output for 66. Because it does all the 2s and then it just does the odd numbers from there forward. And to only return prime factors, there's the prime factors of 66. We can even optimize this. I'm not going to go into it, but effectively we can make it even cleaner by sort of computing things a little more cleanly. And again, it runs even faster. Again, nobody's going to be doing prime factors, but you get the idea. I'm actually controlling something. Let's get into a more practical example where we're actually doing things with data, because again, these previous ones were mostly related to numbers and strings and little diagrams and stuff. What we're going to do is we're going to create a part table, maybe for an airplane, and for each part, we're going to insert the part, and then its parent, and then the part number. So for part 11, its parent is 1. For part 12, its parent is 1. For part 101, its parent is 11, and so forth. And we have a whole bunch of different parents for each part. What I can do with common table expressions, and this is probably our first really interesting example, at least in my part, is in blue, we create a common table expression called source. And we start with part 2, and we actually do a select in the second part of the query after union all, and I say, give me the part number of that part. So I'm basically saying, for the part I have, give me the parent of that part, okay? So it's going to take the part number in red, it's going to say, give me the parent, join to the part table, and then give me the parent. So when I look at part 2, it's going to walk through and it's going to give me all of the parts which have parents of part 2. So all of the subparts of part 2, which is 21, 20, 23, 221, whatever. Okay. And again, at the bottom, I'm explaining that if we use union instead of union all, if there was any recursion in there, we would avoid an infinite loop, which is, I think, very useful in a part example. We can make it a little clearer. We can add dashes to make it kind of, so now you can see the primary part is 2 and the subparts are 2, 21, 22, 23, and then the subparts are the last 3. Okay. The problem is that this is really generating things in ASCII order. This is a little clearer, kind of showing you them as arrays, which is a little cleaner, I think, because the parts, this is a funny example, but normally you'd want some kind of ordering here. And I can now get them in numerical order, which is kind of a little clearer. Now I can see the breakdown of each part and all its parents as I'm running through here. And the full output would look like this. Okay. You can kind of see with the dashes how it works. We can do internal things with Postgres. Postgres has a dependency table. So I'm going to create a table called dep test. And we have a PG depend table inside the system tables of Postgres, which actually lends itself to this kind of digestion of common table expression traversal. So I basically can walk through my dep test, and I can say, show me in the system tables everything depends on it. And of all those things, everything those things depend on, and so forth. So I actually, when I run this, I get two dependencies of dep test, both of which are types. If I don't want to show the parent, I just want to show the dependencies, I can do that. If I add a primary key to the table and I run it again, I now can see the primary key as a dependency. Kind of interesting. If I add a serial column and I run again, I now see the serial column as a dependency. So what I'm doing in this example, the part example was kind of contrived. In this example, I'm actually running the common table expression to traverse through the Postgres system tables recursively. Okay, I mean, you may not ever want to do that, but again, if you have other cases where you need to traverse across through a hierarchy like that, it very clearly shows how common table expressions make that possible. And again, this is the full output of all the dependencies for that, and you can see the parent, the subparent, and the sub-subparent in this case of all of these dependencies in the system table. Okay. To finish out, I want to talk about a customization that Postgres has that is very, very powerful. And that is something called writable common table expressions. That might seem kind of weird to you, but just follow along, okay? The common table expressions as defined by the SQL standard are only select. But because Postgres has returning clauses that you can attach to non-select queries, the insert, update, deletes can actually appear as though they're select, and therefore they can be used inside common table expressions in really powerful ways. So there's two capabilities here of common table expressions. One is that you can actually allow insert, update, delete inside of with clauses that return data that can then be used by later queries. The second one is that you can actually use with clauses that feed into insert, update, and delete statements. There's two different capabilities, and I'll show you examples of each one. So we're going to create a table called RET demo, and I'm going to insert into RET demo 3 random values. And you can see the 3 random values right there. Okay. Now, in the bottom query, I'm going to say select from, well, I'm going to have a with clause, and I'm going to insert 3 more random values into the RET demo, but I'm using the returning clause right here, okay, which is that's my returning clause, right? And I'm returning a value, and what I want to do out here is I want to say of the 3 values I just inserted, I want to report the average of what I just inserted. Kind of interesting, right? Because they're random, you don't know what they are, they're generated on the server. How would you know what they are? Here we're going to return the average of those 3 random values. Kind of interesting. So here we're taking an insert, putting the insert inside the with clause, and then we're using the output of the insert to then feed into the bottom query. Okay. I can do something similar with delete. I can delete all of the random values, but I can also report the maximum random value that I deleted because I've got a returning attached to the delete clause. Okay. In the opposite direction, RET demo 2 allows me to do the opposite. I can, instead of doing the insert, update, delete inside the with clause and then returning something, I'm going to have the with clause generate some data in a select, and I'm going to feed that select into insert, update, delete after it, outside. Okay. So here I'm computing the average of RET demo 2, the 3 random numbers I put in here, and I'm going to delete every random number that is greater than the average. That's less than the average. So any Any random value in RetDemo that's less than the average of what's in RetDemo is going to be deleted, okay? And as you can see, it only left one row because that was the only row that was greater than the average. I can even do it recursively. Here, what I'm doing is I'm saying take part 2, generate all the part numbers for it inside the common table expression, feed that into the bottom query, and delete all the parts, delete part 2 and every part that is a child or grandchild or ancestor of part 2. Child, not ancestor, child. Anything that's a child of part 2, whether it's a direct child or 20 layers down, I'm going to be able to delete those automatically, and that's kind of really useful. I can put both features together, which is going to make your head spin. What I'm going to do here is I'm going to insert 3 random numbers into random 3. I am going to select the average of those numbers. I am going to delete everything that's less than the average, and then I'm going to return what I deleted. Okay? I'm going to compute the average. I'm going to delete everything less than the average, and then I'm going to show what rows were deleted by having the blue returning there is actually returning from the delete, which is returning the rows that I deleted. So the cool thing about this is if you've been doing separate statements in SQL a lot, like, oh, I have to insert, and then I want to do something with the insert, and whatever, now you can kind of bundle them all together. And the nice thing about that is that it's one query, it's one visibility in terms of transactional visibility or query visibility. You don't have to use read committed mode, for example. I'm sorry, repeatable read mode. You can actually have single visibility for all these things together. It's kind of nice. Okay. And here's an example of that. So what we're doing is we're creating an order table. We have an items table. So this monster query here, second query here, is saying insert into the order table my order, return the order ID, and then insert the item that I want, and use the order ID that I generated from the orders table when I add the part that is in that order. And then the bottom query is saying delete everything for that order, and then also return the order ID and delete all of the sub-items, all the items that are part of that order. So again, kind of chaining stuff together. It's really, really powerful. And that's kind of a really creative way of using SQL that a lot of relational systems don't support. And again, it kind of gets over the problem of, oh, I got to do a query, I got to return something, I got to send another query, I got to do something. Common table expressions allow you to kind of bundle that together. We can even go farther. So what I'm doing here is I'm deleting from the order table. I'm deleting from the items table. Remember, I'm joining source. I'm generating source. Here, source 2 is referencing source. But also, what I want to do is I want to insert the deleted order number into a table called old orders. So I'm deleting 2 places, and then I'm also inserting as part of that. Kind of crazy, but hey, it works. So in conclusion, why use common table expressions? Allows imperative processing in SQL. We talked about that. Merging multiple SQL commands and their connecting application logic into a single query, unifying the SQL language, which I think is really cool. Improves performance because you're sending fewer queries, you're not transmitting as much, and you're reducing the parsing because you're only parsing once instead of parsing 3 times. And again, it kind of is nice. It's a little bit of a change in terms of style, but it might be something to consider. As I said before, it uses the same row visibility snapshot as the entire query, because therefore you don't need to use serializable isolation level or repeatable read isolation level in these kind of cases because it's a single query. There is one issue I need to highlight, and that is that up until Postgres 12, until before Postgres 12, these common table expressions were actually behaved as an optimization barrier, which meant that Postgres would always execute the common table expression first and then the query after it. And in some cases, that would make queries slower. It can hurt performance because you can't like join things together efficiently as you would if they were both in the same query. But that's only in Postgres before 12. In Postgres 12 and later, the barrier is only used when it's useful. And you can force a barrier with the word materialize in Postgres 12. So again, I think the major downside of common table expressions, that optimization barrier, fortunately, is kind of going away in Postgres 12. You can still use it if you want to. You can still force a barrier. But in general, you probably would not want to. And Postgres 12 will generate better query plans, I think, with common table expressions than previous releases. So that is what I wanted to cover today. I hope that was interesting. Again, I gave you sort of a big outline of what this thing is and why you should care about it. You might be excited to give it a try. But I think it's kind of interesting. I had trouble understanding when I first heard about common table expressions. I remember seeing a huge query that generated Mandelbrot. And I was like, I had no idea how it worked. I had no idea how everything worked together to make it happen. So what I've tried to do is to be very methodical and start very simple and just build little piece at a time until we started to get into these complex cases. But hopefully it gave you enough background so that they made sense. And over to you, Molly.
Yes, thank you so much, Bruce. We do have a couple of questions that came in. The first one is the syntax used for all SQL databases or just Postgres?
So all the stuff I showed up until writable common table expressions is standard. And it's kind of nice because I know Oracle had its own syntax for this type of behavior, and other databases all had different syntaxes. And fortunately, we never implemented one. We've waited for the standard to come up with one and then implemented that. The writability of common table expressions is specific to Postgres because that whole returning idea was not part of the standard. It's possible they will invent it. The standard will adopt it someday, but I'm not sure.
Okay. The next question that we had was, can CTE be used in stored procedure?
Yes, absolutely. These queries are full class queries, so you could use them in any context.
Okay, great. Another question that we had was, can you inline recursive CTEs by using continuous passing?
So continuous passing, was that the term that was used?
Yes, continuous passing.
Continuous. I don't know what that is. I will say that in Postgres 12 and later, common table expressions will be inlined into the latter query. So effectively, even though if you don't use recursion, right? If you don't use the recursive keyword, we can't inline with recursion. But if we aren't using recursion, that common table expression will be in most cases merged with the query beneath it and run optimized together. The only case that won't happen is if you reference the common table expression more than once in your query. We assume it's more efficient to execute it individually rather than executing it twice inside of a query. So that's kind of how the logic works, that we'll try and inline it if we think it's useful.
Okay, great. So we are having a ton of questions roll in, but I think we only have time for one more. So at this time, if you did ask a question and you are interested in a pair of socks, please drop your address so we know where to find you, where you can get your pair of socks. And the last question we have is, why are window functions useful and can they be done in the client? Yeah.
Well, window functions are, I'm sorry, can you say the question again?
Yes. Why are window functions useful and can't they be done in the client?
Okay, so I assume the question is why are they useful and why can't they be done in the client? A lot of cases, common table expressions can absolutely be done in the client. So you could be doing all this in the client. You could be computing the average in the client. You could be walking the tree in the client. You could be, it's possible to run a whole bunch of queries and just walk a tree by just sending a whole bunch of queries, and for each step of the walk, you have to send a new query. So the idea of common table expressions is that you're pushing the problem to the server. It's doing all the kind of data for you. You can do all sorts of analysis at that server. There really isn't anything there's no reason you have to use them. You could stick with non-common table expressions, do everything that way. But I think it's better, more efficient, and clearer for your application if you can bundle them into common table expressions. It's probably a better solution.
Okay, perfect. So I want to thank Bruce today for taking the time to do this webinar. I apologize for the questions that we were unable to get to. We will be answering them, and the link to finding the questions to all the answers that weren't answered during the webinar will be linked in our follow-up email. This is all the time that we have today. Thank you for joining us, and we will share the recording and the slides as soon as possible. I hope you all have a great day.